All right, I'll kick this off here. And as you know, you met Rosemary yesterday. She's going to introduce you. So for all of you guys, this is the final finale. This will be the 5th presentation we've had for you guys. I hope you've liked the internship lecture series. You got to hear from our president, Dave Olson. You got to hear from John Till, and even got to visit his farm. Some of you guys did. And then you heard Rod Balser's presentation about deep isolation. And then last week, you guys heard Chip Cameron, formerly from the Nuclear Regulatory Commission. And today you get to hear Peterson. Rosemary's going to introduce him. But I really, this should be an outstanding presentation. I hope you guys like it. So Rosemary, why don't you come up here and introduce our speaker?
My name is Rosemary Murphy. I'm an Environmental Compliance Authority here at DWPF. I have a Bachelor's of Science from the University of Washington in Seattle, and I also have my Master's of Science from the University of College Cork in Ireland. I studied abroad. So this is the 11th place I've lived. I'm 33, so I've traveled a lot. I've lived in a lot of different cities, and I've worked in different sectors within the environment. Previously, I lived in Florida, and I've only worked here for two months, by the way. I moved from Florida, where I worked for the Department of Environmental Protection and the Fish and Wildlife. And I also worked in consulting firms, helping with environmental compliance and regulation within their mining sector, and then also just other monitoring and remediation sites. So my overall background is not very typical. Like I said, I've lived in 11 different cities, worked in a lot of different environmental sectors. So my advice to you overall is to take other opportunities that might not be within your goals here as students or college students or master students, because you don't know what those experiences will bring you. So mentors, or I worked as a gymnastics teacher. I gained professional presentation skills. You never think that would come. So just make sure don't shy away from any experiences, because you don't know what will bring you. So I'm going to introduce Dr. Peter Peterson. He's our last lecturer for our series. Dr. Peterson has a robust biography and resume in nuclear energy, nuclear technology, resources, and the environment. After his graduate studies in mechanical engineering at UC Berkeley, Dr. Peterson was convinced that working in the nuclear field was very important, especially in the management of nuclear technology for civil and military competency purposes, and how to improve existing technology and develop new advanced technology. Throughout Dr. Peterson's career, he served as the chief, member, and chaired to numerous advisory committees, startups, and working groups, including, to name a few, the Blue Ribbon Commission for America's Nuclear Future, which was requested by President Obama to recommend policy reviews for a new strategy in the nuclear fuel cycle, and holds the William and Jean McCallum-Floyd Chair in the Department of Nuclear Engineering at UC Berkeley. As the Chief Nuclear Officer for Kairos Power, and Kairos means prompt and timely at a particular time, right now, basically, he has led groundbreaking developments in advanced reactor technology, helping us transition to clean energy. As the former chair of the Nuclear Engineering Department of Energy Resources Group at UC Berkeley, he teaches nuclear energy, serving his mechanical engineering alma mater, aspiring new prospects in the focus of nuclear applications and advancing reactor technology. He's authored over 110 archived journals and 120 conference publications on the topics of passive systems and AP100 reactor designs. Currently, Dr. Peterson heads his research group at UC Berkeley on heat transfer, fuel mechanics, and regulation and licensing for high temperature reactors to help with the improvement of existing technology and the development of new safe technology for future nuclear energy innovation. So Dr. Peterson is especially proud and excited to present here because he helped design the facilities here at DWPF right out of college, specifically Saltstone and DWPF. So really, nuclear is one big giant family, so he's happy to come home and share his experience with you guys. Thanks.
Thank you so much. It's a pleasure to be here. Let me bring up some slides to share And also, I really would like to encourage, I'm going to try to go through these fast enough that we'll have some time at the end for additional discussion. And it's really exciting for me to be able to talk with this internship class because you're sort of at the beginning of your careers. And when I think back on what I was able to learn in internships and then in sort of the early work that I did, which was I worked at Bechtel on the design of the Defense Waste Processing Facility. I learned so much by working with senior people who were experienced. So let me know if this is, let me see if I can get this to advance. Can people hear me okay? Good. Okay, it's just slow. Good. Okay, so let me just confirm. Can people hear what I'm saying? Okay.
Yes, we can hear you.
Perfect. All right. This is just a few photos that provide some sort of background on things that I've done. I've always been very interested in understanding how nuclear infrastructure can be designed, operated, and also decommissioned. And I also have been very interested in how it is as an industry and as a profession, we can organize ourselves to build very large scale projects. And so my initial experience you can see here was actually I was a junior engineer responsible for designing the systems that provided steam and cooling water and other process fluids into the various different vessel systems in the DWPF. And I was able to see the P&IDs and designs that I was working on under supervision of really some amazing senior engineers from DuPont, which ran the Savannah River site back in the day. And they were so experienced and talented. And so working with them, we were able to translate that. And back in the day, we didn't have 3D CAD modeling. And so we built a full-scale plastic model of the entire plant. It no longer exists, but there's still some very good photographs around. I'm really grateful to Savannah River for finding some of those and sending them to me so that I can share them with you. But you see, here's the melter, here's the carousel where the canisters go on. Building this kind of model, I think, actually was one of the things that helped the project end up coming in pretty much on schedule, on budget, and construction, which is pretty impressive because building the model required thinking through a lot of the construction processes that subsequently would be used in the full-scale construction. Since then, I've been involved in a bunch of other types of nuclear activities. And of course, I've taught in this area at UC Berkeley. And so this is the Millstone plant. This was shortly after the Fukushima accident, visiting to understand because this is a sister plant of the one that had the accident in Japan. This is the Vogtle plant, which is nearing completion of construction, just a short distance away from where you folks are these days, and being able to visit and also to contribute to the design of the passive safety systems that are being used in the AP1000. That was really enjoyable. And then I was also selected to be a member along with Senator Pete Domenici and other people of this Blue Ribbon Commission. And I'll talk a little bit about that experience as well in the context also of our national policies for managing nuclear waste, which I think it's very important to place that into context. So what I'm going to do is, first of all, just provide, I know that many of you already have experience within nuclear engineering of some types, but I wanted to give a brief overview of the nuclear fission process. And also the types of waste products that are generated by it and the volumes and stuff. I want to place that into context with other energy sources because that is important. And then I also want to talk a bit about what I view to be some of the current issues and opportunities related to nuclear waste. As you're likely aware, and this is important for Savannah River because we have high-level glass waste that DWPF has been producing that needs to have a destination. And it's been held up largely because I think we don't have a societal consensus about what to do with the spent fuel coming from our commercial plants. And I think that's impacted our ability to develop disposal capabilities for other types of waste, including the defense high-level waste. But let's plan to come back. It's really important, though, to emphasize that nuclear technology is not unique in producing waste. And the photos that you see here is quite interesting. That's a big front end loader. And this is wind turbine blades being placed into shallow land disposal. So all energy technologies require that we mine materials, that we use them carefully and efficiently. But in the end, all of our technologies will generate some types of waste, and engineered disposal of waste is a perfectly acceptable way for us to manage waste, whether it be windmill turbine blades or nuclear waste. So to begin, the discovery of nuclear fission, that is the fact that if you have neutrons and you bombard uranium, especially uranium-235 or other heavy elements with neutrons, that those elements could split. This discovery occurred in 1938. It was initially recognized by Otto Hahn and Fritz Strassmann because what people were doing then was they had the ability to make neutrons, and they knew what neutrons were, and they knew that by absorbing neutrons into different elements, you could create new isotopes, and that some of those isotopes would undergo radioactive decay, and that radioactive decay could make new elements. And so they were trying to make heavier elements, but they kept getting very strange chemistry. And in the end, Hahn and Strassmann were able to confirm that definitively this light element barium was being generated by this reaction. And that implied that the neutrons were causing fission. Meitner and Frisch were able to take that and work through what the implications were in terms of the fission reaction and the amounts of energy that it might release. And they concluded that those numbers were enormous. In fact, they were able to conclude that a fission reaction would release somewhere on the order of about 200 million electron volts. And this is an important number. I'll show you why. So the fission process, when we use it to make energy or to produce new elements, because, for example, the fission process allows us to convert elements like uranium into elements like plutonium. That was one of the early major missions at the Savannah River site, was to produce plutonium. This was for U.S. defense program. And now we're working to clean up from those early activities, and that's a part of what the DWPF is doing. But this reaction, again, you can see it releases about 200 million electron volts, and you get two fission products. There's a distribution of different isotopes and elements that are generated. The thing about this reaction is that it will also generate 2 to 3 additional neutrons, which makes it possible to sustain a chain reaction where on average one of those neutrons goes on to cause another fission, and the other neutrons are going to be absorbed into different materials. And if we're clever about what materials are around that we absorb those neutrons into, we can develop advanced reactors that will have remarkable types of capabilities in terms of advanced fuel cycles. Now, the energy density from this reaction, this 200 million electron volts at macroscopic scale, is kind of a big number, 8.2 times 10 to the 13th joules per kilogram. That's not a very easy unit. So the one I prefer is to say that if we have a 1,000 megawatt electric power plant, that is a power plant that can produce enough electricity for about 1 million homes, it will consume about 3.2 kilograms of nuclear fuel per day. That's about 7 pounds, right? And in this process, we also generate a variety of different radioactive wastes. Of course, there's the fission products, and this is sort of a rough schematic of what that distribution looks like. And some of the important ones include, for example, strontium-90, which is a 30-year half-life, cesium-137, which is 30 years, technetium-99, and other things. So there's a lot of skill and competency at Savannah River in understanding both how these fission products behave and other materials, and then how to manage them safely. We also generate a variety of activation products. And as I mentioned, the absorbing neutrons into uranium produces heavier elements such as americium, neptunium, plutonium. And these elements, some of them have long half-lives, but as noted below here also, if one recycles them, it's technologically feasible to fission them and to convert them into shorter half-lives. It's also safe to place these into geologic disposal. We'll come back and discuss that in just a moment. We also will have neutrons absorbed into structures. This will generate generally low-level wastes that have moderate half-lives. We have the capability to place these types of wastes into the safe disposal in low-level waste disposal facilities. I know that, for example, Scott Kirk has worked with the Waste Control Specialist facility that's in Texas. That's a fantastic facility for this sort of disposal type of mission. And then we also have the coolants. We should also recognize that in the life cycle of energy systems, that there's additional environmental impacts that come from the mining of the not just the fuel material, but also the materials that are used in construction. And we need to think about the entire life cycle, particularly when we're making comparisons with other energy sources, including wind and solar. So let's go ahead and compare this to energy from fossil fuels. This is a combustion reaction. And in this combustion reaction, we're taking dominantly oxygen, which we take from the atmosphere, and hydrocarbons. In this case, I'm showing coal, which is approximately 1 carbon, 1 hydrogen. There's obviously some other stuff, and there's actually, in coal, there's quite a bit of dirt in coal, which is why you end up with quite a bit of ash after you burn the carbon and the hydrogen there. This combustion reaction releases about 160 electron volts. That's not million electron volts, that's electron volts, and generates carbon dioxide, water vapor, and then there's other things that come out from the combustion process. So this is the energy density. It's about 29 megajoules per kilogram, or that same 1,000 megawatt power plant will generate of order 7 million kilograms per day, or will consume 7 million kilograms per day of fuel. And because these quantities are so enormous, there's no practical way for us to manage the waste products from that combustion except to discharge them into our environment. And if we're careful about it, we can control it in ways that reduce the public health impacts. But in the end, these are very large amounts of nitric oxide, sulfur oxides, ash, and of course, our major concern at this point is that we need to transition away from generating large amounts of carbon dioxide from energy production. So the use of fossil fuels as feedstocks for fertilizers and plastics, and there's many beneficial things that we can do with the hydrocarbons that we can harvest from various different sources. But the one thing that is problematic is burning these materials to generate heat. There's better ways to generate heat, and in particular, nuclear fission is a fantastic way to generate high quality, high temperature heat, which can replace the need to burn fossil fuels. And so in the mining, of course, we need to think about all of the things that happen in the mining of the fuel and as well as the construction materials. Good. So again, please just interrupt with any questions as we're going along. And okay, so I just, not to spend too much time, you'll see speakers sometimes show this type of graph, which Human Development Index, the quality of life in countries that like France, Norway, the United States, there's where incomes are sufficient that one has broad access to all sorts of services. This is what humans should be aspiring for all people to have the ability to live at this level. Of course, that's not uniform around the world. And there are countries where deep and pervasive poverty exists. where public health infrastructure is poor, where education infrastructure is poor. And the question is, what is necessary to transition the part of our population in the world that lives this way to have lives that have the quality that we take for granted, for example, in the United States. And the strongest correlation is with access to energy. So our ability to provide and produce more energy is really critical if we have a goal of assuring that all people around the world can live lives that have all of these things that we would list in terms of a human development index. So with this thought in mind, let's think about this question of energy production. Now, an interesting thing about nuclear fuel is that even though with our current reactors, we only utilize about 1% of the actual energy content in the uranium that we mine, because dominantly we're fissioning the element uranium-235, which is about 0.7%. We're producing modest amounts of plutonium and some of that fission, so maybe about 1% of the uranium that we mined is actually converted into energy. Advanced reactors using uranium and thorium can increase that. But even with that, when you look at the cost of uranium, because uranium is abundant around the world, and it's also, we mine large amounts of uranium. Some of it's mined in Russia. That's a bit concerning these days. But large amounts are mined in Canada, in Australia, and actually the United States has abundant uranium resources as well. We need to think about increasing our domestic production for a variety of different reasons. What I've done here is I've worked through what the costs are today to procure uranium for fuel, and I've converted it into dollars per million BTUs of heat, because this allows us to make a direct comparison with natural gas. And of course, these days, natural gas has been shooting up to about $10 per million BTUs. But you can see that nuclear heat is very, very inexpensive. And if you use the uranium more efficiently, of course, you conclude that the cost of the fuel is negligible. Moreover, you can have on site a year to a year and a half reserve of fuel. That's actually typical at nuclear power stations, whereas a typical fossil plant running on coal might have 3 or 4 days, maybe a week of fuel on site. So there's a variety of things that can disrupt supply chains that we've observed. What nuclear does is it gives you secure access to energy even when supply chains are not working seamlessly. And what about emissions? Well, this is a comparison of the CO2 emissions per kilowatt hour of electricity generation in Germany over, and it hasn't changed much in Germany and in France. And you can ask, with Germany building so much wind and solar, what's going on with these numbers? And the short answer is that you see the very, very high volatility in the output. That's because intermittent sources of electricity, like wind and solar, do have to be backed up by something that is dispatchable. And in the case of Germany, that's dominantly coal and natural gas. In France, which built out way back in the 1970s to 80s and transitioned to being about 75% nuclear, average carbon emissions are over 10 times less. And they've been doing that for decades. So that shows that it is feasible to essentially fully decarbonize national energy supplies. And it takes about a decade of dedicated effort to build out the infrastructure if you go down the nuclear path, which is what France has done. So how about waste? Let's start to place it into context. In 2014, about 10% of world electrical power came from fission of uranium. That energy from the fission of uranium is equivalent to burning about 1 billion tons of coal. The entire spent fuel generated by all worldwide reactors during that year, if you were to hypothetically collect it all together, and this is a photograph of Cal Memorial Stadium at UC Berkeley, and if you were to place it on that football field you'd get a layer about 1.3 meters deep. And so then I said, well, how do we get a picture to show what that might look like if it was coal? And of course, 1 billion tons of coal, that's a bit taller pile. Of course, again, this is hypothetical because nobody's going to build a 230-kilometer high tower of coal. But if you did, you'd have to get back up into space to be able to sort of see what it would look like, because this is what it would look like. So the sort of the neat thing in thinking about how it is that we manage the very small volumes of low-level and high-level waste that come from the use of nuclear technologies and nuclear energy. And this includes things such as medical and industrial applications of radioactive materials. Many lives are saved because of our ability to do nuclear medicine and to use nuclear materials in medicine, and that does generate wastes. Those volumes are so small that it's quite practical for us to place them into safe disposal. And this is something, there's a lot of expertise at Savannah River about how to do this in environmentally responsible ways. In the case of course, coal, what we're doing is the opposite. We're mining large amounts of stuff out of safe geologic sequestration. Reversing this process makes sense. So I also wanted to place into context these volumes. If you went back here, this is of the order of maybe, I think, 8,000 tons per year of spent fuel. I'd have to go back and check the specific numbers, but it's a modest quantity. We can compare that with solid waste generated just by municipal industrial activities. I think that and these numbers these are hundreds of millions of tons per year in various different parts of the world. So really large volumes. In the developed world, these solid wastes are handled by and large quite responsibly. We have efforts to recycle as much as we can. And then the remainder is placed into engineered disposal facilities, landfill facilities. The big issue really with solid waste is the fact that in these countries that have the low development index, there's not the resources available to responsibly manage the solid waste. And so the practice of open dumping, that is just in urban areas, just trying to move stuff and dump it out in the open, that's pretty pervasive around 30% of the world. And having access to abundant and affordable energy makes it feasible to do the things that are necessary to also responsibly manage these other waste streams. And that's another reason why it's so important for us to move forward in these directions. Okay, so how about geologic disposal of waste? I suspect that many of you have heard of this facility called Yucca Mountain. It turned out to be highly controversial because of the way that we went about picking it. And there's also, I think, technical issues. Well, we've been able to engineer this Yucca Mountain repository system to be able to comply with the stringent 1 million year safety standard. Doing that required quite a bit of investment in engineered barriers such as alloy 22 and titanium. That said, if we think through the question, because all of the waste, all of the high level waste and spent fuel that the United States has generated to date could in principle be safely placed into disposal in Yucca Mountain. And the worst case consequence of the poor performance of that repository would be that because that repository is located above the water table, over tens of thousands of years, rainfall seeping down through the mountain could potentially corrode through canisters and then release small amounts of radioactive material that could be carried in. And it's possible that one could contaminate sort of a narrow plume, maybe 50,000 to 100,000 years from now, across the Amargosa Valley. And that would mean that you would either have to treat this water or put wells, move your wells away from this water. Now, to place this into context, when we look at what we've done with chemical contamination, there are thousands of wells already in the state of California that have concentrations of various different chemical contaminants, which are of concern for public health. And this is why we treat water, and this is why we monitor water from wells and stuff. So the incremental impact on long-term public health and difficulty from having geologic disposal of nuclear waste is going to be very small. And this means that geologic disposal is a responsible approach, particularly when you start to get innovative. And you had a chance to hear from Rod Baltzer. He's amazing, as are Rich and Liz Muller, who are the co-founders of this company, Deep Isolation. What's really cool here is that they're using advanced modern technology that has been developed for horizontal drilling. And what they realized was that by going horizontal with a deep borehole, you solve two major problems with the older vertical borehole concept. And one of them is that in a vertical borehole, you've got enormous range of pressure because pressure increases as you go deeper and deeper. The fluids, the lithostatic pressure and stuff goes up. And so you begin to get concerned with the pressure on canisters causing canisters to crush. Of course, if you go horizontally, the pressure is constant, and that's a really good thing. Also, geologic media tend to be stratified horizontally. So if you go down a kilometer, which is much deeper than is feasible with mined repositories, and you can find actually the optimal layer to go into, and then you can go a mile or more in a horizontal direction. And that means that you can also locate waste on sort of optimal locations. So I think that the main thing to point out here is that innovation is feasible in this area, and that we should really be thinking of the management of nuclear waste as being something where there's the potential for us to come up with dramatically better ways to both reduce the quantities of nuclear waste that require disposal, and then also to do innovative things to provide safer, less expensive disposal. The other thing that this sort of disposal method does is it eliminates the need for underground mine facilities. And those are actually expensive to construct and to operate. They require large ventilation systems. There's a lot of safety requirements on things like fire and other things that makes working underground more hazardous than many other types of environments. And all of that factors into increasing the cost of mined repositories compared to this sort of borehole approach. So what should we be thinking in the US about nuclear waste? Well, let me start with what I consider to be the good things about nuclear waste, because in fact, the one way of looking at nuclear waste, which may sound counterintuitive until you think about it a bit, is that nuclear waste is actually the best thing there is about nuclear energy. And that's because it's such small quantities, and we have the technology to manage it safely so that it doesn't cause any negative or extremely small negative impacts on public health, safety, and the environment. And this is because the volumes are very small. The other thing that's very good about nuclear waste is that we internalize all of the costs for the disposition of those wastes into the price of electricity, into the prices that people pay for electricity. This is not the case with fossil fuels. In fossil fuels, there's large environmental and public health impacts that aren't put into the cost that people pay. And this means that those costs are borne, it's a subsidy, by people out in just the local communities around these facilities that have to breathe the air and have to live in an environment where the waste can disperse over long periods of time. We also know that safe disposal of nuclear waste is feasible. We have multiple low-level waste facilities around the United States, including, I think that the Waste Control Specialists facility, which is one of the newest ones in Texas, is sort of like that's a really good example of how to go about developing and implementing engineered facilities, new engineered facilities. The waste isolation pilot plant is also fantastic. It's in a deeply bedded salts in southern New Mexico, and it has allowed us to clean up a lot of the defense complex Currently, it is limited to accepting transuranic wastes from defense programs. Technologically and from a safety perspective, that facility could also actually be used for other types of waste. And one of the options, if we went through the necessary work on policy, would be to think about using it also for high-level waste. But this is something that we need to think about going forward as we rethink our strategy on waste in general. And then we also know that if you do have a policy and you're committed to the disposal of spent fuel, it is feasible to develop geologic repositories for this purpose, because both Sweden and Finland have done this successfully. So what's bad? Well, the first is that because nuclear waste is controversial, our regulatory framework for managing it is not logical. That is, the biggest problem is that the classification of nuclear waste, the approach to saying this waste is of a certain type, is not based on the specific hazards, but instead it's based on where the waste comes from. And this creates a whole set of problems. Internationally, it's much more common to classify nuclear waste based on specific hazard, and therefore to set your requirements for disposal based on the specific characteristics of the waste rather than on where it came from. And this is something that hopefully we can correct over time going forward. It's also true that many people, particularly opponents, but also proponents of nuclear energy, overstate the hazards posed by nuclear waste. There are people that are very enthused about the potential for advanced reactors to burn spent fuel, and that could be a good thing. Unfortunately, they'll also commonly imply that that spent fuel is somehow really, really dangerous, and that their kind of reactor is absolutely essential to burn up that really dangerous waste. That's not a constructive way to talk about spent fuel, right? So I think if you have both proponents and opponents who are both telling all the public that nuclear waste is dangerous, of course everybody's going to believe that it's true. And of course you're going to lack a consensus about what to do with nuclear waste. So let's dive into that question. Well, the first thing is, as I mentioned, we internalized the costs of waste management into the cost of nuclear electricity. And we had a fee up until actually 2013 or 2014 that was collecting 0.1 cents per kilowatt hour from nuclear electricity generators. And the average revenue was about $750 million per year, which is actually, if you think about it, that's quite a few kilowatt hours of power generation. And the total volume of spent fuel at this point, I think we've got about 80,000 tons or so. And that's been 20% of US electricity generation for like 35, 40 years, a remarkably small amount. Because we stopped work on the Yucca Mountain, Congress has not appropriated money since about 2009, and instead that fund has just been accumulating interest. And it's fascinating; it's now above $45 billion, and the interest payments on that fund are now double what was being collected pretty much at the maximum point in terms of revenues. And so the fund is growing so fast just because of the amount of money that's already in it. It's actually plausible that when we finally figure out what we should be doing with spent fuel, and I'll talk a bit about that, that when we update the fee adequacy assessment report, we'll conclude that the existing balance is enough to cover all the costs for the existing spent fuel in terms of disposition. And also that probably there's enough money there to pay for the additional spent fuel that utilities might generate. That is, the United States might never need to restart collecting a fee. And wouldn't that be interesting if utilities didn't have to pay anything, because essentially you could argue they overpaid early on? I'm confident that if we go down the path of doing things by like developing borehole disposal, which has very low cost and it's quite safe, that we could actually be in a position where the existing fund is sufficient for the federal government to do all of the things that it needs to do to manage the spent fuel. So I think our big problem today is that we actually do not know whether spent nuclear fuel is a resource or a waste. What I can tell you is that the current technology to recycle spent fuel, for example, the way that France currently does that, which is to use Purex reprocessing to separate plutonium and uranium, create high-level waste forms with the other transuranics and fission products, very compact waste forms, and then to recycle the uranium and plutonium back into light water reactors. It's very challenging to manufacture fuel for light water reactors that contains plutonium, because plutonium is substantively more toxic than uranium, and so the controls, glove boxes, other things are significantly more complicated. And so it's really the challenges in being able to manufacture fuel to go into our existing commercial reactors that makes recycle uneconomic. But that does not necessarily hold true for advanced reactors, which have fuels which are much easier to manufacture from recycled material, and also that don't require that recycled material to be decontaminated to the same level that is necessary to use that material for light water reactor fuel manufacturing. And a really good example, because it's active technology development by the startup company TerraPower, is a molten chloride fast reactor. And this is one where the fuel is uranium and plutonium chlorides mixed in a chloride salt liquid fuel that would be circulated around, and you'd actually fission the uranium and plutonium in situ in this molten salt. Now, this is a technologically challenging type of reactor to develop. There's going to be a very small scale prototype that will be constructed. It's called the Molten Chloride Reactor Experiment at Idaho National Lab. I think it'll be about 100 kilowatts that would demonstrate the technology. I cannot tell you today whether they'll be successful. I'm working at a startup company that's also involved with molten salt reactors, but they're of a different type. It's a thermal spectrum pebble fuel type of reactor. But what I could tell you is that if TerraPower is successful in developing this type of reactor, it will be very affordable to recycle spent fuel back into it, because all you need to do with the spent fuel is convert it into chloride salts. And we know how to do that quite well. So this I think what we just don't know today, whether we're going to be successful in developing advanced reactors where the economics of recycling fuel from existing spent fuel to provide fuel for the new reactors will actually be very attractive. And in that case, we would want to recycle spent fuel in the future into these types of reactors. There would still be residual waste, but we have technologies such as borehole disposal that can be used. All of this points to the need for a set of policies that recognize the fact that we don't know today whether we should place spent fuel into disposal or not. And how can we do that? Well, the first thing is really to facilitate further innovation in this field. And I love this, a little bit old slide, but you've got all of these different startup companies that are working on advanced nuclear technologies, fission, fusion, fast spectrum reactors, thorium reactors. There's just an enormous amount of work that's going on. And we also know that as a country, we have the capability to innovate these days in ways that perhaps we didn't believe were possible. We lost faith in our national capability to solve really challenging technical problems. And I like to use this slide that shows the space shuttle, which was an amazing type of technology. I compare it in terms of technological complexity and challenges also, including having some kind of bad accidents, to what we were doing with our very large light water reactors and such. And the space shuttle ended up being very, very expensive. So what happened was that we we began to innovate. We had NASA actually put in place a different contracting mechanism, Commercial Orbital Transportation Services Program. There were dozens of startup companies that were looking at how to build better rockets. And of course, one of them we know today was SpaceX. And today, so in 2006, sort of back when we knew that we had to get rid of the space shuttle, the United States had completely lost all commercial space launch revenue. There was no business at all. We had no rockets which were affordable. And there was this little startup company called SpaceX that had been founded in 2002. They were able to get this a small one-engine rocket up into orbit by 2008. By 2012, they delivered cargo to the International Space Station. By 2015, they had demonstrated that they could re-land the first stages of their rockets, which was pretty amazing. By 2018, they had captured over 50% of the world market share for commercial space launch. And of course, today they're building starships in Texas. It's just phenomenal. So I like this because this shows that you can do things that nobody believed were possible, right? This is just amazing, and this is the sort of thing that I think this kind of innovation, the United States is the place where it can and is happening. Let's see if we can make that happen in nuclear technologies as well. So, what about the question for spent fuel? Well, the first thing is that we have very good technology to store for interim storage of spent nuclear fuel. And we've developed the technology. It's very cost effective. It's entirely passive. And it makes sense for us to use this as our current method for managing spent fuel. We should try to develop consolidated facilities so that we can ship stuff from decommissioned plants to those locations and stuff. And let's not rush to build a repository. Instead, let's go ahead and do the necessary research and focus on defense high-level waste where there's unambiguous, the high-level waste coming from facilities like the DWPF, coming from the waste facilities that are starting up at Hanford. That stuff nobody wants to recycle, obviously. That's the stuff for us to focus on. And so let's figure out ways to get, place it into disposal, including developing and demonstrating borehole disposal, because it could be more effective and less expensive, at least for wastes that are not bulky and such. And so with that, I'm going to open the floor for questions and discussion. We've got a little bit over 10 minutes, and let me see if I can end the show and stop sharing, and then ask. I'm happy to discuss any and everything about things that we've covered in this presentation. So please, questions.
This is Scott. I have a question for you. And also the audience that's online, if you guys have some questions, start raising your hand so we don't miss you. But Per, my question is about your role at the Blue Ribbon Commission. I think that's the final report was based on a number of different stakeholder meetings that you guys had across the country. The first one I attended, it's at the Willard Intercontinental Hotel in Washington, D.C. And in Carlsbad, where you guys visited the waste isolation pilot plant. That visited. But that whole process culminated in a report, and I think it took about 2 years to develop that report. And I'd like for you to talk about some of the outcomes of that report, one of which was borehole technologies and exploring that as a possibility for a repository as opposed to a mine technology. And then the other one was consolidated interim storage. The thought was if you could consolidate and dry cast store spent fuel, then that would give us time to find the best ideal location for the next repository and the technology to do it. But I think one of the most salient points that came out of it was consent-based licensing. And that way you don't want to site one of these disposal facilities in a region or in a community that doesn't want to be there in the first place. And you have to build consensus in order to get that consent. So could you elaborate about the mission of the Blue Ribbon Commission and what you thought were the most important parts that came out of the Blue Ribbon Commission in regards to its recommendations?
Yes, and of course, it was quite an honor to be able to serve on that commission. What had happened was that there had been a political decision in the Obama administration to cease work on Yucca Mountain, and back in that time, the Senate Majority Leader was from Nevada, and that Senate Majority Leader, when he had first joined the Senate, that was in 1987 when Yucca Mountain was down selected by Congress in a process that was, let's say, not what you would consider to be a fully fair process. So it was logical. It was sort of logical what was happening. The commission was asked to explore alternatives, a strategy going forward. The thing that I think I learned from the process that was the most important was that holding public meetings and listening to what people care about is extraordinarily important, particularly for engineers. And not everybody here is an engineer, but what I can tell you is that, and I'm guilty of this too, engineers, because we use technology to solve societal problems, tend to assume that we know what people care about in society. And if you go out and listen, oftentimes you discover there's other things that they're worried about that are equally important and logical. So I think that that's helpful. So the commission did make a set of recommendations, including moving forward to develop a second repository. The commission didn't make recommendations one way or another about Yucca Mountain itself. But within Congress, there was just not a consensus. There was a subset of Congress that wanted really to restart Yucca Mountain and focus on it. There was a part of Congress that did not want to do that. And what we ended up with was essentially a stalemate where Congress has not done anything in this intervening period. As I mentioned, I think the silver lining is, first of all, there's now an enormous amount of money built up in the Nuclear Waste Fund. And so if we come up with a policy that can develop better consensus, which I think is one that acknowledges that the interim storage of spent fuel is the appropriate thing for us to do, along with some consolidation and the technology development, and then serious work on advanced fuel cycles, that's probably the best path for us going forward. Those were some of my primary insights. It was fantastic to visit Carlsbad and the area around the waste isolation pilot plant, which is actually not that far from Waste Control Specialists, because it was, there are communities, especially those where there's a history in nuclear technology, like around Savannah River and stuff, which are so knowledgeable about the technology, and they support responsible work, and that includes developing capabilities for engineered disposal of the small amounts of waste that require disposal from nuclear technology. I guess those are my primary insights. So next questions.
Not a question. This is really an opportunity for me to brag on the staff. And as you may or may not know, the Department of Energy reinterpreted the definition of high-level waste. And it's really based on that you should be able to classify the waste based on a hazard that it poses to public health and the environment. So
Yes.
if the waste is class C or less, for low-level waste, it can be reclassified as low-level waste. And I'm somewhat simplifying this, or if it doesn't require the same degree of isolation as provided by a geologic repository, it can be reclassified as low-level waste. And we did the first proof of principles for the recycled wastewater from the DWPL. And so that was the first proof of principle that the Department of Energy selected. And that recycled wastewater, at least samples of it was shipped to WCS, and it was dispositioned as Class B low-level waste. And then now we're working on the second proof of principle, which is some of the legacy equipment. So I know that you plan on coming here in the fall. And when you do, I'm really pleased to introduce you to the staff. I want them to meet you, hear more about your work, and we can share more with you about hopefully, which is going to be our second successful proof of principle demonstration. Go ahead, Per.
I am so proud of this. This is exactly what we need to be working on because we know that the original regulations were kind of logical, but that was before we understood very much about how to classify the hazards of waste and what the implications were for appropriate disposal. The use of engineered surface disposal facilities like WCS. This is the correct way to handle, especially a lot of the legacy wastes from our defense programs, because the hazard of those wastes has diminished so much, and it's so small now that by all types of performance standards, engineering, you can demonstrate that you can get the necessary safe isolation for those materials. So this is extraordinarily important because it opens up our possibility to both accelerate the cleanup and decommissioning of these old legacy facilities left over from the weapons program. And it also opens the possibility for us to do it at substantially less cost to taxpayers. And then finally, we should be thinking about how to repurpose all of these existing sites because they will remain brownfield. And the logical thing to do with them is to build new infrastructure, industrial infrastructure, reestablish a lot of our domestic manufacturing capabilities and build energy production facilities and recycle facilities and stuff in these locations. We just can't do that until we've gotten rid of the old stuff and dispositioned it properly. This is fantastic work that you're doing.
Engineers, physicists, we get what's right when it comes to the physical sciences, but what we have not done is integrate the social and the political science into the selection of the final decision. So with that, I'm going to open it up to the audience for our interns. Who's going to ask the first question?
Okay. I see one coming up.
I see a gentleman over here who asked a ton of questions to every one of these lecture series, and I'd like for you to think about what your first question is going to be. And come up to the front and introduce yourself.
Looks like we have a question in here.
Oh, right here.
Right here, yep, that's perfect.
My name is Willie Oods. Willie Oods. I'm gonna hear that.
You can read
Oh, you
it yeah, for him.
Okay. I guess my first question would be, where do you work at?
So I split my time evenly between UC Berkeley, where I continue to teach and do research. I am working more on topics related to nuclear waste. We have a fantastic new project there from ARPA-E, a DOE ARPA-E program called Onwards, which was working to develop advanced waste forms for advanced fuel cycles. And also we're working on what we're calling a universal canister technology that will be suitable for disposal across a full range of different disposal types of facilities, both mine repositories and also borehole disposal. So that's half of my time. The other half of my time, I'm the chief nuclear officer for a startup company, as mentioned earlier, Kairos Power. We're now at about 280 employees, and we're developing a high temperature reactor technology that uses a molten salt coolant. And we're going to be constructing the first demonstration reactor in Oak Ridge, Tennessee, so not that far away. That means I do get out to the Oak Ridge area fairly frequently, and that makes it easy to get over to Augusta and then to come and visit the site. And that's the reason that we're planning to do that in the fall.
Okay. I have another question.
Go ahead, ask another question.
Okay, so my other question is the work that you do similar to the work that we do here when we remove waste?
Oh, there's a lot of overlap. Basically, the set of competencies to work with nuclear materials, a lot of what we're doing is actually based on technologies that were prototyped and developed early on at Hanford and Savannah River. And one of the things with the high temperature reactor technology that we're working on now is because it's intrinsically low pressure, it doesn't require a high pressure, low leakage, high pressure containment building like say the AP1000 technology does. And there's potential for substantial cost reduction. The type of facility that you would use for these low pressure, high temperature reactors looks a lot more like the types of facilities that you have at Savannah River, because the reprocessing DWPF facilities, those are all intrinsically low pressure systems, and it's much easier to get stuff in and out and do maintenance in a facility like DWPF. A pressurized water reactor containment building, everything you're doing in it is like trying to build a ship inside a bottle, because you have very limited access. And I view the filtered confinement type of facilities as being much easier, because you look at like DWPF and it's like a shoebox. You can take the lid off and you can do all sorts of stuff, and you can put the lid back on. And so the ability to do maintenance, the reduced cost of construction, there's enormous potential in just all of the things you need in terms of radiation protection, quality assurance. Those, you'll find that across all of these different nuclear sites, and those skills translate between these different types of activities. So at any rate, I'd say there's a lot of overlap.
Okay, thank you.
Any more questions? Yes, Brandon, come on up.
Hi, my name is Brandon. You touched briefly on uranium mining. I was wondering if you could speak a little bit about kind of the hazards and environmental impacts associated with that and how it compares to something like coal mining.
That's a really, really good question. And of course, the practices for mining have evolved substantially. In the early days in the 1950s, a lot of the uranium mining was done in ways that today we would not consider to be sufficiently safe for workers. And it also involved quite a bit of hard rock type of mining. So you had high radon levels down in the mines. There was not a focus on providing a lot of ventilation. And the other issue is that the uranium ore contains a lot of daughter products, decay products from uranium, and you have to be careful about how you dispose of the mill tailings. So there's a legacy from the early uranium mining that we're still working to clean up. And it was largely, I don't think it was evil intent. That wasn't it at all. It was more a lack of knowledge. So the modern practices for mining of uranium create far less environmental impact. And in particular, there's technologies called in situ leaching, which essentially can, because uranium, the reason that uranium is concentrated into ore bodies is because in chemically reducing conditions where you have organic material and stuff, it becomes much less soluble. So if you can come in with an oxidizer like peroxide, you can actually pull the uranium out of formations without having to do mining. This is similar to, because the fracking technology is another one which reduces the impact compared to mining and creating mill tailings and stuff. In the longer term, also, the potential to harvest uranium out of the oceans is quite real. And that's something that merits continuing work. And then finally, the fact that we only use 1% of the energy content of uranium, and we could extract energy from thorium as well, means that there's potential to dramatically improve the efficiency with which we extract energy from uranium and thorium. And then we've got fusion in the longer term too, which may bear fruition. All of those things for me suggest that both the environmental impacts from the production of the fuel, as well as the costs of the fuel, all of those are going to continue to get better. I do not expect nuclear fuel to ever become expensive, because I think our ability to increase conversion ratios, improve technology, as it has over the last decades, will continue to advance much more rapidly than resources are depleted in terms of uranium. So that's a quick overview, but it is important to acknowledge that in the early days, there were practices which today we would not repeat, and there's a legacy that we need to manage responsibly. At the same time as with modern mining, we want to use modern practices that reduce the environmental and public health impacts. And they're definitively much smaller than mining coal. I mean, this is orders and orders of magnitude, smaller environmental impacts from uranium versus coal. Good.
We're gonna ask a couple ask my staff. Do you guys have any questions that you would like to ask a pair?
Yeah, I'll ask. So what was your inspiration for naming, Kairos Power? Is it because it is prompt and timely?
I cannot claim credit for the naming of the company. That is the CEO, Mike Laufer. And his inspiration was the fact that Kairos means an opportune point in time. And it just seemed appropriate. Because of that, pretty much in this company, we name all of our experiments after Greek gods. And I don't have a good ability to remember names. It's not the thing I'm the best at doing. So I'm not sure. For me, using Greek names doesn't help a lot. But that said, it was Mike Laufer, and I do believe it's a very good name, and it reflects not just what our company is doing, but also more broadly what our nation is going to be able to do in this coming decade in terms of reviving our capabilities to do things in nuclear technology space in ways that will be really impressive. Anyhow, that is the origin of the name.
Let's open up to the audience online.
We have two questions. One is from Merlin, if you want to unmute.
Yes, Merlin, ask your question.
I see. He says I don't have a microphone. So let me see if I can. Oh, here we go. Just to add to the long list of uranium mines around the world, Niger also has a huge deposit of uranium, so we won't run out of uranium anytime soon. And then, yes, I concur with that. As I mentioned before, there's so many different ways that we can both increase production of uranium, and I think we should also look at thorium seriously because it's yet more abundant, and also use it more efficiently. And because it's already so inexpensive that 36 cents per million BTUs compared to like $10 for natural gas. The scarcity of uranium and high uranium costs is not the thing that I worry about. I think we need to get better at developing and deploying sophisticated technological systems. And there's a lot to be learned from companies like SpaceX in terms of how to drive down manufacturing costs while meeting high quality levels and such. There's a different set of problems. We also need to make progress in this area on nuclear waste. And I think to the extent that we can continue to be successful in cleaning up legacies waste from the early phases of nuclear technology development, and the fantastic things that, for example, Scott was talking about with respect to reviewing waste classification and rationalizing so that we can accelerate disposition and developing a societal consensus that there's real big benefits for us to do that, and that the local communities that are taking on responsibilities around hosting facilities for the disposal, just as communities develop landfills for solid waste. I mean, we have to do this to be responsible. That we come together as a society and say, if we work together, we can decarbonize our economy. We can have abundant, affordable, clean energy so that the cost of electricity is not something that people worry about in their day-to-day life, among all of the other things that one has to think about: education, housing, other things. Having energy be expensive, which we're experiencing right now, is not good for society. But we need to be able to produce energy in ways that are clean. And this is really the thing that all of us should be working on this coming decade to enable so that it can happen. Very good. Maybe
Today's presentation, I hope that all of you liked it. Per, I thought it was outstanding. It's a pleasure to meet you, especially an expert of your merits. Anyway, thank you very much, and we look forward to hosting you down here. And I will follow up with you on a potential tour date sometime in the fall.
fantastic.
All right,
Thank you, everyone.
thank you very much.
Great. Take care.